We turn now to our last topic in our last two topics, I suppose, in rotational motion, which are rolling without slipping and angular momentum. So let's start with rolling without slipping. We talk an awful lot about rolling without slipping in physics. And the reason we often talk about rolling without slipping is not just because it happens a lot in the real world, but it also happens to be a very special case. So when we say rolling without slipping, let's imagine we have a wheel or a ball or something. And let's imagine that it is rolling. It's rolling this way. And it's got some angular velocity omega. As well, we can also say that the center of mass of the object is moving. The center of mass of the object is moving with some velocity v. And I'm actually going to say velocity vcm, with the velocity of the center of mass. Well, it turns out that the rolling without slipping condition, when we know we're rolling without slipping, is a really important one. It's one that we know already. It's v equals r omega. So when are we rolling without slipping? Well, when the velocity of the center of mass is equal to r times the angular velocity of the object. And this, by the way, has a peculiar consequence, which is that if you look at the velocity of different parts of the wheel, it turns out that the center of mass is indeed moving with this velocity v that we talked about. But if you think about the points on the edge of the wheel, points up here are also rotating, v equals r omega, this way, but the point at the bottom is also moving backwards at a velocity v equals r omega. And so what you actually find, if you look very carefully at these situations, is that the center of mass of the wheel is moving at a velocity v. The very top point of the wheel is in fact moving at a velocity of 2v, and that point of contact with the road or surface or whatever is in fact momentarily not moving. And this is a little strange to people. They always are a little perturbed by that. But I'm going to make you a couple arguments. The first argument is, this is why we call it rolling without slipping. That point has no velocity just for a moment relative to the road. If it did have a velocity relative to the road, it would be sliding one way or the other on the road. It would be slipping and skidding a little against the surface. And instead, it's not. It's just briefly in contact with the road before it gets picked up and moved over. So this contact point is actually not in motion. And so there's a couple consequences to this, and a couple important things that we have to deal with when we're talking about rolling without slipping. The first, of course, is this rule that we already have, which is v equals r omega. This is our rolling without slipping condition. It's a very familiar thing. It's going to be really important to us. The second point is, of course, that contact point is the contact point has v equals 0. And so this has some other consequences. For instance, if there's friction, which there usually is if you're rolling without slipping, it means that it's static friction, not kinetic friction. This is, by the way, why skidding is so dangerous in a car. Your tire is actually rolling along the road because of static friction. Once it starts to skid, once it starts to slip, kinetic friction kicks in. Kinetic friction is weaker than static friction. So once you start to skid, it's actually harder to control your car because you're relying on a weaker force of friction. The other thing is that if we're tracking the energy, the kinetic energy of an object that is rolling, we can actually separate out the two motions. And what we can say is we can treat it as being a rotation around the center of mass plus the kinetic energy of the motion of the center of mass. That is, if we're looking at the kinetic energy of something rolling, it actually has two components of that kinetic energy. They're not vector components, but kind of two parts of it. There's a rotational kinetic energy and a translational kinetic energy. And so let's actually take an example of this, and we'll do a little conservation of energy question that's kind of interesting, which is to say, let's take, for the sake of argument here, we're going to take a sphere, a solid sphere, so a ball. Reminder for a sphere, ICM is 2/5 mr squared. We're going to assume it has a mass m and, you know, a radius r. And we're going to let it roll down a hill of height h, and we're going to see what happens. Well, the first thing, this is conservation of energy, that you might say, well, is we're probably going to start with mgh worth of potential energy, and you would be right. It still descends a distance h. If we want to know, you know, how fast is it moving when it gets to the bottom of the ramp. Now, the important thing here is that it's not just 1/2 mv squared anymore. All of that energy isn't going into translational motion. Some of that energy is now going into rotational motion. Now, in this case, 1/2 mv squared, we know some things about I. We know that the I for a sphere is 2/5 mr squared. And just like we have on some of the problem sets, we're also going to get rid of omega by exploiting v equals r omega. So I'm going to replace this omega squared with v squared over r squared. All right, a couple things are going to happen here. I'm going to cancel out all of my m's. Turns out that the mass doesn't matter. My r squareds and my r squareds go away. And it actually turns out in this case that the radius doesn't matter either, which is a little peculiar. So we get 1/2 v squared plus, let's see, oh, I missed one cancellation. 1/2 plus 1/5 v squared. So 1/2 plus 1/5 happens to be 7/10. So we end up with our velocity at the bottom being root 10 over 7 gh. And I just want to note something real quick. 10 over 7 is about like 1.43428. We are used to, by the way, you know, you might remember from way back in the day from conservation of energy, right? If we just had like a block sliding down a ramp, it would arrive at the bottom with a velocity of root 2 gh. So it's sensible to ask, hey, look, our ball, 10/7 is less than 2. Our ball arrives at the bottom slower than we would expect, slower than a non-rolling object. And there's two main arguments that you could make here. One of those arguments is of course actually that if you want to roll, there's got to be friction. So friction is going to slow us down. If there's no friction, the thing will just glide down without rotating. But the second argument is also that I find a little bit more compelling, is where does this energy go? Where does this energy go? This mgh goes, previously, it all went into kinetic energy, right? We had mgh equals 1/2 mv squared. It all went into translational. Now, our potential energy has to go to two places. It has to go to rotational and to translational. And so because some energy is going into rotation, there's less energy left over to let it go quickly. And in fact, we can drive this point home, perhaps, by doing a quick comparison with a different shape. So let's say we have a different shape going down our ramp, same ramp. But now we're going to put at the top of it a different shape. We are going to put, say, a hoop, a hoop or a hollow cylinder, which has an I of a full mr squared, not 2/5, but 1 mr squared. And if I do this calculation real quick, and I want to know with what speed does this get to the bottom, well, I still have mgh, 1/2 mv squared, but now I also have 1/2 I omega squared. I have two forms of kinetic energy to track. My I is, of course, a full mr squared. And my omega squared is still v squared over r squared. I can still get rid of all my m's, my r's cancel. And so I get gh equals a half plus a half, or just v squared. So I find that v equals root gh, which again, root gh is less than root 2gh and is less than 10/7. Root 10/7 gh. So the hoop actually is even slower than the sphere, even slower than the ball. And why is it even slower than the sphere? Why is it even slower than the ball? Well, the eye for the hoop is bigger than the eye for the ball. And what's kind of curious here is, I know in this case I've kind of said that they're the same mass, the same radius. Notice that mass and radius don't actually feature at all in the final equations. It turns out that what really matters a lot for the movement of rotating objects is actually this coefficient. That for the sphere is 2/5 and for the hoop is just 1. So a hoop of any size or any shape, there's an argument to be made that no matter how big or small, a hoop has more rotational inertia than a sphere, and so is always going to be a little slower down the ramp. The eye is bigger. It takes more energy. It takes more rotational kinetic energy to get it moving, and so there's less energy left for speed, less energy left for translation. All right, so now we're going to talk about our very last topic, which is angular momentum. We turn our attention now to angular momentum, which is, of course, the rotational equivalent of normal momentum. The letter we use, though, is L, because there's no P in momentum, so there's no L in momentum either. It's the letter L. Now, you might be wondering how we define angular momentum. There's a couple, the most basic way, and I know there's going to be a couple different forms based on what we need. It is a vector, and if you're into vectors, it's the cross product of r and the linear momentum of an object. I want to be a little bit more specific about that, which is that there's a couple different forms depending on whether you have a point particle or whether you have a solid object. Kind of like as we were considering I, we had to do different things. If we have a solid object, or excuse me, if we have a point particle, it turns out that this has a pretty simple thing. It's r times the perpendicular component of momentum. So in this case, if I've got my little object here, it would be mass times the perpendicular component of velocity times r, mvr. Now, of course, I got to figure out a little bit what the component of my velocity perpendicular to my radius is, but it's mvr, where specifically we're looking for the perpendicular component of velocity. I do want to point out that, of course, if that perpendicular component of velocity is r times omega, so you can also think of this as mr squared times omega. And I do like the mr squared times omega perspective because if you've got a solid object, like a disk or a rod or something, it turns out that the momentum here has a really satisfying form, which is L equals I omega. And the reason why I think this is a very satisfying form is it really resembles P equals mv, but with all of those rotational quantities swapped. So instead of momentum, it's linear, or instead of linear momentum, it's angular momentum, mass to rotational inertia, velocity to angular velocity. So L equals I omega. I do just want to point out that mr squared omega is kind of the same, right? If you recall, for a point particle, it's just mr squared is the I, so you kind of get that I omega connection. Anyway, I don't want to sit and belabor you too much with all of the things that angular momentum does, because frankly, it does most of the same things as linear momentum. First of all, it is a vector. And the directionality is the same as for omega and alpha and torque and everything. So if I have an object rotating like this, my angular momentum vector will in fact be along the axis like that. In general, it's a cross product. So in this case, my object would be kind of going directly into the screen here. It is a vector, and it is conserved, just like regular momentum. It is conserved if you have no external torques. So just like regular momentum is conserved if you don't have any external forces, angular momentum is conserved if you have no external torques. As a quick side note, by the way, this is a little extra. We can make a lot of other connections, right? We learned for linear momentum, right, about impulse, about the change in momentum. We learned that change in momentum is either force times time, or if the force is changing, it's the integral of f dt. Well, it turns out that a change in angular momentum is just torque times time, or if the torque is changing, the integral of torque dt. Similarly, you can have you can have kind of a rotational concept of work as being torque times a change in angle. This is force times distance, or the integral of a torque over some angle. This is the idea of like rotational work. It changes rotational kinetic energy. So just some neat little asides. You don't really need those, but I would be remiss if I didn't show them to you. So angular momentum is conserved, and I just want to note that this is separate from linear momentum. So even though they both go by the name of momentum, they are actually totally distinct quantities. Angular momentum and linear momentum are both conserved, but they are conserved separately. That doesn't often come up in this physics class, but it is worthwhile. So what that means is if I have some kind of, two rotating objects that are touching or something like that, my initial angular momentum is going to be equal to my final angular momentum. So I want to look at a couple quick examples of this. So let's imagine that I have a spinning disk, like a turntable or something. And let's imagine that it is spinning at some initial speed omega 0. This is a disk, so it's going to be have an I of 1/2 mr squared. And what I'm going to do is I'm going to drop onto it a ring of the same mass and the same radius, but it's a hollow ring. It's not a solid disk. And I'm just going to drop this straight onto the turntable and kind of see what happens. It's going to skid a little bit, and then they're going to start to spin together. So in this case, again, just like with regular momentum, I can look at my before and after. Before, all of my angular momentum, L equals I omega, is with my disk. So my initial momentum, angular momentum, is going to be 1/2 mr squared omega 0. And my final momentum, they're going to stick together plus I ring omega final. They're going to stick together and move together. And that's going to give me 1/2 mr squared plus mr squared omega final, which is 3/2, 3/2 mr squared. So if I set these equal to each other now, right, I have to have conserved angular momentum. Pretty much everything goes away except for the 3, and what I find is my omega final is 1/3 of my initial omega. That is, it slows down due to the collision, but it's not about the difference in masses, it's actually about the difference in I's. So I actually lose a lot more velocity. Even though they have the same mass, they have dramatically different moments of inertia. This, by the way, you may have been told this at some point in your life. The classic example of conservation of angular momentum, right, is of course like a skater who's spinning around. They've got their arms outstretched, and they're spinning around with some omega, and then they pull their arms in, right? They pull their arms in really tight. Well, there's no external torque. They're the only one that's done that's changed their motion. It's all internal. And so what happens is when the radius of their arms decreases, their moment of inertia drops a whole lot. Well, if they have the same momentum and I goes down, omega has to go up. So their omega final is much, much greater than omega initial. So they pull their arms in, reduce their radius, reduce their I, and massively increase their omega. We could do other examples, right? You know, on your problem set, you'll see something, you know, you could imagine having a stick. It's pivoted around the middle, and you could, like, you know, shoot a little wad of gum at it at some initial velocity, and it sticks to it, and the thing starts to rotate, right? So here we would have to, you know, figure out what our R was, you know, how far out on the stick is it going to hit. So we'd have to start with an initial momentum of mvr, and then that would end up being, you know, some I omega final. So we'll go over some examples of that in class. But the net result here is that L equals I omega, unless we're dealing with a point particle, in which case mvr is probably a safer way to go. And that, just like regular momentum, it is conserved. So you can always do initial momentum equals final momentum. And like I said, we'll take a look at a whole bunch more of those in class.